Krug coming at you for part 2 here of our lecture on stars and galaxies. So last time we talked about what stars were. We talked about the seesaw battle between gravity and star energy during a star's life. We talked about that special F word, no, not that one, but nuclear fusion, which happens at the centers of stars to make them very, very hot and bright. And then we talked about not only star brightness and physical properties, but the spectacular HR diagram. So that is where we're going to pick up today. So this lecture is going to cover pages 4 to 7 of the notes, and then you're going to have 10 more questions to answer on Google Classroom. So let me go ahead and share my screen with you all. Having fun with my friends. All right, so here's where we left off last time, a little visual for you. So recall, this was our HR diagram, and what was special about this, everybody, is it allows us to classify all stars in the universe based on 2 fundamental physical properties: their temperature, which increases towards the left, and their brightness or their magnitude, which increases up. Remember, for magnitudes, the negative numbers are actually brighter, and the positive numbers are actually dimmer. So we would have very hot, very bright stars up in this corner, very bright but very cool stars in this corner, very dim and cool stars in this corner, and finally over here at the lower left, we would have hot and dim stars right there. So let's start going through what I call our star family in space. Remember, teens, these stars, as far as we know, are not actually living, breathing entities like you or I, but we talk about them being alive because it makes it easier for us to understand. Violet, don't go so high on that swing, baby. You'll fall off. Sorry, just shooting this from my back porch so I can keep an eye on the little Krugs here while I am lecturing. Okay, so our first family are the supergiant stars. So let's take a look here. That covers the top of the diagram. On some HR diagrams, you'll actually see a bubble joining these 2 groups together. So those are blue and red, and right away we're in for a surprise. These are newborn or baby stars. And the reason that might be surprising to you is with humans, generally the older we get, the bigger and bigger we get, until people get really old and then they actually start to squish back down as their spines compress together. But overall with people, the older we are, the bigger we are. These stars, though, are just born really, really big. So the blue variety is up to 1,000 times larger than our sun. But the red flavor are the real whoppers. They have up to 2,000 times larger than our sun. So we've got 2 blanks here. Take a minute, figure out what would be the overall magnitude, the brightness, and the temperature for supergiant stars. Okay, so the overall magnitude, all of them, everybody, are going to be very bright because either blue or red, notice they're all up high on the diagram. But our blue supergiants are going to be very bright and very hot since they're over to the left of the diagram. Our red supergiants are going to be very bright but cool since they're over to the right-hand side. Some examples which we've learned in class, we saw Sirius in the wintertime sky along with Betelgeuse. You might remember that was the reddish shoulder of Orion, the mighty hunter. And then we have Vega and Antares, the heart of the scorpion, from the summer sky. Those are our red supergiants. So supergiants are very young stars. They're very, very large. And we're going to see later on, they live very surprisingly short lives. Next up, we have giant stars. So at this point, you might be thinking, okay, it seems kind of weird that big stars are young. Giant, that sounds big. That must be really young, right? Wrong. These ones we are going to call our grandparent stars. We're going to see they get big somewhat like supergiants, but it happens very, very late in their lifetimes. We're going to see they live a different life cycle. So most of them are red. Let's take a minute right now. Let's look back up at the red giant bubble. Remember, not supergiants now. We are highlighting this group right here, our red giants. What type of temperature and brightness would they have? All right, so their overall temperature Red giants, and you can even see they throw a yellow giant in here, but the group is mostly called red giants. They are going to be cool, because notice they're over at the right-hand side, just like the red supergiants. And we could say they're bright. They're not as bright as red supergiants. Notice they're around the 0 magnitude line here, but they're a little bit above average. So we could say these are bright but cool stars. Okay, our final group on this page are main sequence stars. I like to call these the moms and dads and sons and daughter stars because they make up most of the stars in our stellar family. Like, think about your own family at home. Some of you might have a newborn at home, or some of you might have a grandparent who's old enough that he or she moved back in with your family. But most of your family is you, your siblings, and your mom or dad. And that's the same way with main sequence stars. In fact, they make up 90% of all the stars in the night sky. It is a huge range. You can see that bubble snakes the whole way through the diagram from the upper left to the lower right. And so up here in this corner, we are going to have very bright and hot stars. Down in this corner, we're going to have very dim and cool stars. And notice, teens, where our sun is. It is almost average right in the middle. So it's not too hot, it's not too cold, it's not too bright, it's not too dim. Our sun is very average. And recall, this is a common theme from section 4. Our sun is pretty plain and regular. And initially, as humans, that can make us feel bummed out, right? Because we want to feel like we're really special and unique. But think about it. If our sun really only arose due to a really wildly unique set of circumstances, which was unlikely to repeat itself, there'd be a pretty good chance we really are the only life in the universe. But just the opposite is true. Our sun overall is very humdrum and regular and average, like many other stars in the sky. So if we as humans are here and our planet Earth is here, that's actually very exciting. That means there's a really good chance for other life being out there. So this is our main sequence. It's where the sun is right now. So overall magnitude, we could say very, very bright down to very, very dim, and overall temperature, very, very hot to very, very cool. That's our main sequence. Finally, everybody, we have dwarf stars. Now, I like to call these the great-grandparents. So the red giants were the grandparents. The dwarf stars are the great-grandparents. So first, let's talk about the only color that officially appears on the HR diagram. Those are your white dwarfs. So let's take a minute to see if we can figure out what their brightness and temperature would be. Notice this group is down here, and we are going to see in just a bit that white dwarfs are intimately linked with the main sequence and the red giants. In fact, this is going to be one of the final star stages of our own sun someday. Because they're down in this corner, we could say that they are very, very hot because they're over to the left, but they're also very dim because they're down at the bottom. And that might surprise you because you might think that all hot stars would be really bright. But in reality, for white dwarfs, they are so small that they're just not giving off very much light despite their temperature. So these are around the size of Earth, and they're the hot core remains of stars. Now, our next group are called red dwarfs. Now, you might think to yourself, wait a minute, I didn't see them anywhere on the HR diagram. Technically, they are there. They're basically a subgroup of the main sequence. So if we look back up at our big diagram, the red dwarfs are basically the stars right down in here. And if you actually thought about this diagram three-dimensionally, like piles of stars stacked up on the different piles to represent how many there are, it might surprise you to learn there would actually be a humongous pile down in this lower right corner for the red dwarfs. Unfortunately, our eyes, you might recall, are a little bit biased. We don't see the color red nearly as well as we see blues and whites on the sky. On top of that, red dwarfs are very, very small, as the name implies, so they're very dim. In fact, as far as I know, there is not a single red dwarf on the sky that humans can actually see with the naked eye. Even the closest ones need decent-sized telescopes. And yet, if we could see all stars evenly, the sky would be absolutely covered in red. So because they're down in this corner, we know they're going to be very dim, and they're also going to be very cool. Now, red dwarfs, you would think, despite their size, or because of their size, they would live very short lives. But it's almost like they know they don't have very much nuclear fuel and they use it very, very sparingly. Astronomers estimate a red dwarf could live anywhere from 20 billion the whole way up to 200 billion years. Now think about that. Our universe, as far as we know, is only about 13.7 billion years old. So that means these tiny red dwarf stars could outlive our current universe many, many times over. All right, our last two colors, everybody, are not on the HR diagram. And there's a reason for this. To be on the diagram, you have to generate your own heat and your own light, which is why we don't see planets on the diagram. So this group are called black dwarfs. This is basically the burned out core of a white dwarf star. So we learned during lecture 1 that stars like our sun can fuse the whole way up to about the element carbon. And so carbon, everybody, is very, very black in color. So when these white dwarfs finally burn out and they run out of fuel, they don't kaboom like a supernova for a high mass star. They basically just fizzle out. And it's basically a charcoal briquette about the size of Earth, still floating in outer space. And ladies, this is kind of exciting. A couple years ago, a team of astronomers thought they had found a white dwarf which had actually crystallized. So what that means is somewhere out there floating in the deep reaches of outer space, there is actually a single diamond about as big as the Earth. So those are black dwarfs. That's the eventual end state of our own sun. Now another type, and if you watched our Planet X Nibiru lecture, if you remember that one from class, you might be familiar with brown dwarfs. It sounds similar to black dwarfs because the colors are similar, but it's actually very different. A black dwarf is a star that was alive, but since died out. A brown dwarf is basically like a star which has never been born. It's basically a big ball of gas and dust, but it doesn't quite get big enough to ignite nuclear fusion, which makes it a star. So why do I show an image of the planet Jupiter here? Because some astronomers actually consider Jupiter to be a brown dwarf. So the borderline between big planet like Jupiter versus small star is very, very nebulous. So these are basically failed stars. They aren't on the HR diagram. And because they're really only radiating in infrared, one could be dangerous to our solar system if a rogue brown dwarf ever happened to lurk its way in. So those are brown dwarfs. Okay, so does every single star go through every star stage? Will every single star be a supergiant, giant, main sequence, white dwarf, red dwarf, brown dwarf, black dwarf? The answer is no. Stellar evolution depends on how massive a star is when it's born. Now, tragically, teens, astronomy is always underrepresented in standardized exams. But I can tell you, if they ever give you an astronomy question on like the SATs, or here in Pennsylvania, we have the Keystones, it's almost always about stellar evolution. Don't be intimidated. It simply means how stars live their lives. So on this next page, I'm going to show you a diagram of stellar evolution. And this is important because for the previous 3 pages, all we've been able to see are snapshots at different places in a star's life. Now you basically can see the home movie, how it all works together. So let's talk about the high mass chain first. Overall, this entire chain is very short and violent and chaotic. For a supergiant, it may be as short as 2 million years, which obviously for us humans would be an eternity. But for stars, it's like the blink of an eye in the cosmos. So a red or blue supergiant is going to get so massive, and it's going to be ravenously chewing through its nuclear fuel, fusing bigger and heavier elements in its center until it gets the whole way up to iron. We know iron is the one element on the periodic table that cannot be fused for more energy. So that seesaw between gravity and star energy that's been precariously balanced in an instant will flip towards gravity and the star gets crushed. This implosion then creates a tremendous kaboom, one of the biggest explosions we have possible, called a supernova explosion. It is so big, in one split second, it will give off more energy than our own sun will during its entire 10 billion year lifetime. A supernova, everybody, is so energetic, if one happened within 30 light years of the Earth, it would absolutely fry the Earth and strip off its outer atmosphere as the wave of radiation hit us. But fear not, there's no supergiants that close that are going to supernova anytime soon. Now, sometimes, because we were talking about a solid core of iron, it can survive. It can get compressed into matter as tight as the laws of physics will allow. This is called degenerate matter, and that is a neutron star. Basically, in the explosion, all the free protons and electrons have combined into neutrons. It is now packed so tightly together that a single teaspoonful of a neutron star will outweigh an entire mountain on the Earth. If it begins to spin, it will give off radio pulses, pulse, 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 and that is called a pulsar. However, if a neutron star is not spinning, gravity can cruelly flip-flop the seesaw one more time and implode it to form the mysterious, the powerful black holes, which we'll talk a little bit on our final page of notes. So this entire chain from start to finish is very short, violent, and chaotic. Notice at the supernova explosion, we have what I call a recycling arrow back up to stellar nurseries. What's left after a cloud, or what's left after a supernova? We have a cloud of gas and dust. In what nurseries are stars born? Clouds of gas and dust. So in this way, everybody, star stuff can get recycled. And the same has definitely happened for our own sun. When you look at the spectra, the unique light fingerprint of our sun, we see that it has iron in it. But there's a problem. Our sun never gets big enough to actually fuse iron in its core. So where did the iron come from? It turns out our sun is basically a second generation star, which astronomers somewhat confusingly call a population 1 star. So very long ago, the original generations of stars were supernovae. They were supergiants. When they exploded, they spread their stellar ash across the cosmos, and then our sun rose from some of that ash like a phoenix, and that's why it's incorporated materials from older stars. And again, as the popular astronomer Carl Sagan once said, we are truly made of the stuff of stars. Even the iron that's coursing through the blood in your veins right now, at one point was forged in the nuclear furnace of a supergiant star. Okay, let's talk about the average to low mass chain. In contrast with the high mass chain, everybody, this entire sequence is going to be very long and gradual. It could be upwards of 10 billion years for a star like our sun, or for a red dwarf, even 200 billion years. So today, we are right here at the main sequence. This is where our sun is, and it's got enough fuel in the tank to fuse here for another couple billion years more. But eventually, the quantity of helium in our sun's core is going to start to grow. And that seesaw between gravity and star energy, for the first time, is actually going to tip towards star energy. And our sun is going to start to expand outward into what is called a red giant. So someday, if our descendants cannot figure out a way to physically move the Earth away from the sun, our sun could actually engulf us whole. But do not fear this. It is still billions of years away, and astronomers already have at least one idea on the drawing board as to how they could physically move the Earth away from the sun. But hopefully by then, humans have already taken to the stars, and we're beginning to colonize other star systems. So this red giant is going to keep getting bigger and bigger and bigger until it just kind of poof. This is not a kaboom. This is simply a poof, as it peacefully blows off its layers in what is called a planetary nebula. The name itself, everybody, is a little bit of a misnomer. That means a deceiving name. It actually has nothing to do with planets, but when the first ones were spotted by astronomers through eyepieces of early telescopes, they looked like blue and green disks like planets, and so the name stuck. Notice, just like the supernova explosion on the other side, we have to draw a recycling arrow back up to stellar nurseries. What's left after a planetary nebula? Cloud of gas and dust. What's a stellar nursery? Cloud of gas and dust. So again, in this way, star stuff can be recycled. Now, if you all look very closely right here at the center of the planetary nebula, notice a little white spot. That's where our white dwarf comes into play. This is the white hot core that's still burning after a giant poof blows off its outer layers. So if we journey back up to our HR diagram, everybody, we could map out stellar evolution for a star like our sun. We are here on the main sequence right now. Eventually, our sun will expand and we will reach the red giant region, and then it will poof, blow off its outer layers, and we could draw an arrow down to the white dwarf region. Notice we did not draw any arrows up to the supergiants because they live their own lives as very, very massive stars. So our sun will burn on as a white dwarf for another couple thousand years until it will finally run out of fuel and just fizzle, and that is where we get a black dwarf. So someday our sun will be a charcoal briquette floating out there in outer space. So this entire chain from start to finish, very long and gradual, billions and billions of years. Notice I didn't mention the one mysterious arrow going from white dwarf over to supernova explosion. This is the one and only time that a low mass star can supernova, but we'll talk about that in the final lecture. Okay, I think I just have one page to go here before it's time to ask some questions. So now everybody, let's talk about the deaths of stars. We are going to see that even though stars are all born in similar ways in stellar nurseries, they will die out very differently, like we just talked about on the previous page. So let's talk about stars like our sun, average to low mass stars. Near the end of a very long life, this could be billions of years, that seesaw between gravity and star energy, which has been nicely balanced, starts to rock back and forth. When gravity is stronger, the star gets smaller. When star energy is stronger, the star gets bigger. So bigger, smaller, and just a poof. Not a kaboom, just a poof. Peacefully blows off its layers in a planetary nebula. Now here in semester astronomy, we keep nebulae pretty simple, just two types, dark and diffuse. If a nebula is giving off light, either the gas inside it is so excited that photons are being stripped off, or there's stars inside that are illuminating the gas, we call that a diffuse nebula. If, however, we just have a tower where there's no light given off, that's a dark nebula. Here we have a beautiful example. We learned this one in the winter sky. This is the Horsehead Nebula, and you're actually seeing both types. The horse's head in the foreground is a dark nebula, but the only reason we can see it is back behind it. Think about it three-dimensionally. Here's the horse head, then here's the illuminated cloud back behind it. That's our diffuse nebula. So this is what will happen to our own sun someday. Okay, let's talk high mass stars. Near the end of a short life, only a couple million years, this star is left with an unfusible iron core. Once again, this means for the first time, it can no longer resist the ever-present crush of gravity. The seesaw gets flipped, the star gets crushed, then kaboom! We have this enormous supernova explosion. Officially, it is called a type 2 supernova. Now, you see a vocab word highlighted here from section 1, the Big Bang. The reason I put this, we have to understand not every single cloud of gas and dust that you see in the cosmos is an X marks the spot where a star died out. At 13.7 billion years old, our universe is still young enough that some of those clouds of gas and dust are simply left over from the Big Bang. So afterwards, if the core survives as solid iron, that can be a neutron star. If it starts to spin and pulse, it gives off radio pulses, and that is called a pulsar. So why did I include a diagram here, an illustration of creepy little gray aliens? Well, the first time a team of astronomers found a pulsar, they were actually optimistic that they had found the first evidence for alien civilizations. Because what does a pulsar give off? Pulse, 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 a patterned radio signal. What do astronomers in the SETI program, Search for Extraterrestrial Intelligence, look for sometimes? They look for patterned radio signals. And so initially they had cataloged this object as LGM, which stood for Little Green Men. But soon they found out, probably a little to their disappointment, that it wasn't really aliens, but it was basically the spinning core of a once massive star. But they were probably still pretty excited because they had found a brand new object that astronomy did not know existed, a spinning neutron star called a pulsar. Or, last thing we're going to talk about today, if gravity tips the seesaw one more time and implodes the neutron star, that's where we get the mysterious, the powerful black holes, essentially bottomless pits in space-time. At the lower right, if we could imagine Albert Einstein's four-dimensional space-time and actually see it with our eyes, this, everybody, is what a black hole would do to the fabric of outer space. It bends and contorts it so much that basically the sides of the black hole are so steep, everything falls in, and nothing, not even light, the fastest thing in the universe, can escape. That's why black holes are called black. Light and matter go in, they do not come back out. What's really amazing about black holes, everybody, is they so distort the fabric of space-time that time itself almost comes to a halt around the perimeter of a black hole. Perhaps in the future, we can explore the outside of a black hole. And as long as we don't cross what's called the event horizon, the theoretical boundary of a black hole, we would be able to escape from it. But as soon as you journey across that boundary, your escape velocity, the speed you would need to travel to get away from the black hole, would actually exceed the speed of light. And since according to Einstein, nothing travels faster than light, you would go in, but you could not come back out. Now, just to end today, let's just say this happened in the future. Let's say you and a group of friends are on a futuristic field trip and you're hovering outside the black hole. You could see the event horizon, and for starters, nobody's entirely sure what it might look like. Some astronomers think it would be pitch black, and just within the last year, astronomers believe they have officially imaged the first event horizon of a black hole, and it was black. Others think some event horizons could basically be shiny like a mirror ball, and they're reflecting the whole environment around them. But let's say one of your friends wants to journey across the event horizon. Maybe even you yourself do. So what would happen? Well, against the better wishes of your friends, let's say you push off and you cross over the horizon. At first, you wouldn't feel anything different, and you would become the first human in history to truly see what the inside of a black hole looks like. But we have a problem. You would have no way of telling your friends, even if they're just a couple feet away from you at first, on the other side of the event horizon. If you tried to tell them with words what the inside of a black hole looked like, as soon as the words came out of your mouth, they'd get sucked into the black hole. If you tried to take a picture of one with your cell phone and then show your friends the picture, as soon as the light left your phone screen, it would get sucked into the black hole too. If you went in feet first, you would get stretched out like Gumby towards the singularity, the black hole center. If you went in head first, you get stretched out like a cone head. And all this stretching and squishing of your poor body would heat you up millions of degrees, and you would likely get incinerated before you ever got close to the center to see if any wormholes to other parts of the cosmos existed. Now, your friends would not see this terrible demise. They would see something even stranger. Some physicists believe they would see a ghost image of you on the event horizon as you went across. So if you went across that boundary like this, they would see that image of you frozen there for well over a century, long after you were gone. And then it would just get dimmer and dimmer and dimmer and fainter until it finally disappeared. It sounds wild, but physicists tell us that's the type of crazy physics that would exist around the boundary of a black hole. Okay, everybody, thank you so much for listening along. I'm going to take you through the 10 questions right now. This is going to be assignment 2 for the Stars and Galaxies notes in Google Classroom. It'll be questions 11 through 20. It is not a locked assignment, so you'll be able to pause this video and go back and forth as you answer. So here we go. Question number 11. This star group of newborn baby to young stars are consistently very high magnitude, but they're either very hot or very cool, depending on their color. Name that star group. Number 11, feel free to pause the video. Number 12. This group of stars is also large, but it arrived at this juncture far later in life. Informally known as grandparents, they are bright but cool. Name that star group. Number 12. 13, simple math question for you teens. If 90% of stars are part of the main sequence, in a random sampling of 40 stars, how many will be within the main sequence on average? 90% of 40 stars. Number 13. Number 14, I call this dwarf destiny. This color of dwarf star is actually on the bottom of the main sequence, and they are the most numerous, longest living stars in the universe. Number 14. Number 15, dwarf destiny 2. Never getting massive enough to jumpstart nuclear fusion. These balls of gas lurk silent and dark, not emitting light of their own. These are stars which were never born. Number 15. Number 16, examine the stellar evolution diagram in our notes. In what environments are all stars, whether large or small, born? Where are stars born? Number 16. I have some delightful birds at my bird feeder right now. It's been fantastic. Also squirrels. They're my nemesis. Number 17. This chain of our star life cycle is very short, violent, and chaotic, and can end as a pulsar, neutron star, or black hole. Number 17. Oh, did I forget number 16? Oh, the squirrels distracted me. I bet I did. I bet I didn't say 16. Okay, 16. Examine the stellar evolution diagram in our notes. In what environments are all stars, whether large or small, born? That was number 16. Okay, back up to number 18 now. Stars like our sun are not massive enough to supernova at the end of their lives. Instead, they will poof and blow off their outer layers in a low energy explosion called a what? Number 18. Number 19, because of their pulsing radio pattern, astronomers who discovered the first pulsar initially thought they had found what? Number 19. And finally, number 20, fill in the blanks. Black holes are called black because their blank is so strong that not even blank can escape. Number 20. All right, sorry for the mix up there, but I think we are in good shape now. Thank you all for staying tuned in. Sorry this was a longer lecture, but there's just so much awesome stuff out there in deep space that we definitely need to learn a little bit about it. So if you haven't done so, please answer questions 11 through 20 in assignment number 2, and there will just be one final lecture, third and final lecture of the last part of our notes for the year as we conclude stars and galaxies. This is Mr. Krug. Have a great day. Peace.